Swayam Prabha. Digital India. Educated India.
So, welcome to the 14th lecture on cryogenic engineering, and what we have been dealing is related to gas liquefaction and refrigeration. In the earlier lectures, we have covered several topics related to this particular gas liquefaction topic. In the earlier lecture, we talked about ideal thermodynamic cycle, in which what we know is whatever gas is compressed gets liquefied. So, all the gas which gets compressed gets liquefied, and that is why it is called ideal thermodynamic cycle, which normally cannot be realized in practice. The first modification of that happened in a cycle called Linde-Hampson system. It has got a heat exchanger in it, and this heat exchanger is used to conserve the cold. In this system, only a part of the gas that is compressed is liquefied. So, if we compress X gas, only 5 to 10% of that gas will get liquefied, and the remaining gas in the cold condition will go back to this heat exchanger, and it gives the cold to the incoming compressed gas, and thus the cycle continues. So, the Linde-Hampson cycle or system was the first modification from the ideal thermodynamic cycle, and then came several modifications of the Linde-Hampson system itself, and one of which is pre-cooled Linde-Hampson system, in which the liquid yield and the figure of merit gets improved by pre-cooling the working fluid using an independent refrigerating system. So, this pre-cooled Linde-Hampson system, what happens, we got one more auxiliary system to the major system, and this auxiliary system runs a refrigeration cycle which pre-cools the gas when it enters the heat exchanger. So, basically what is done is pre-cooling, and thereby the liquid yield and the figure of merit gets improved. This was studied during the last lecture, and the highlights of this particular lecture are, in a pre-cooled Linde-Hampson system, the liquid yield Y, what we call as, and the figure of merit are dependent on the refrigerant flow rate. M dot R is what is the refrigerant flow rate we call as in the auxiliary circuit, and the liquid yield Y and figure of merit depend on this M dot R. Also the compression pressure and the pre-cooling temperature. So, there are three major parameters, which is M dot R, compression temperature and the pre-cooling temperature. The yield of the system increases with the increased in the refrigerant flow rate and the compression pressure. So, this is a natural output which we understood from the earlier lecture, that the Y or the yield increases with the increase in the refrigeration flow rate. Naturally, increased refrigerant flow rate means increased cooling effect, and the compressor pressure, if we increase the compression pressure also, in that case also the yield increases. So, one can understand that as the flow rate increases, we get more benefit in terms of having Y. In this system, however, the mass ratio R corresponding to maximum yield is called as limiting value. That means, one cannot go on increasing the refrigerant flow rate M dot R. It has got some limiting value, and we have talked about in detail what this limiting value is all about. So, this limiting value is a function of compression pressure also. So, if we increase the compression pressure in the major circuit, in the major system, the value of limiting ratio also increases. That means, you can admit, you can have more and more mass flow rate in the auxiliary circuit or in the pre-cooling circuit. So, the relationship between the value of R and P2 or the compression pressure was shown during the last lecture. It was done using a problem or a tutorial, and we could draw various curves. We could understand what is this limiting value of R as a function of this compression pressure. From this, we understood that work per unit mass of gas compressed increases with the increase in refrigeration flow rate and compression pressure. It's very directly one can understand from this, as the flow rate increases, we have got two compressors now. One is a major system, one is a pre-cooling circuit. So, as the refrigerant flow rate increases, the work per unit mass of gas will increase. Also, if the compression pressure increases, work per unit mass of gas compressed will increase. But the work per unit mass of gas liquefied decreases with the increase in the refrigerant flow rate and the compression pressure. This is the most important thing. Why are we doing all this thing? Because we want to decrease the value of W upon M dot F. That is, work per unit mass of gas liquefied, and that is the whole objective of this pre-cooling circuit. Also, the figure of merit increases with the increase in the refrigerant flow rate and the compression pressure. So, whole exercise was basically done in order to decrease the value of work per unit mass of gas liquefied or increase the figure of merit with the increase in the refrigerant flow rate and the compression pressure. With this background, what we have understood, what we have done during the last lectures, the outline of this present lecture is again on the same topic of gas liquefaction and refrigeration system. In this system, in this particular lecture, what we are going to talk about is Linde dual pressure system. As the name suggests, it has got Linde two pressure systems, or we got two devices or two compressors and two expanders to be specific in this particular cycle. It also again is a modification of the Linde-Hampson cycle with dual units existing in the cycle, in the system. What we are going to study about in this particular lecture is what is the liquid yield in this particular case, what is the work requirement in this particular case. There should be some advantages, and we are going to study all these advantages. And lastly, there are various parameters, and we will do the parametric studies. But this parametric study I am going to carry out again as we have done previously using a tutorial, because here we understand with the values how to solve the problem. At the same time, we can draw various curves ourselves. So, this is what is going to be studied in this particular lecture. Mathematically, the work requirement for ideal isothermal compression process is given by W dot is equal to m dot R T1 log P2 by P1. This is the work of compression for an isothermal process. What does this mean? The work requirement decreases either with the decrease in mass flow rate or with the decrease in compression ratio. So, in this equation you can see there are three parameters, m dot, T1 and P2 by P1. Suppose the compression process is being carried out at a given temperature or at room temperature only, we will not consider T1 option open to us, because we want to carry out the process of compression always at room temperature. In this case, if I want to decrease the value of W, that is work of compression, I can touch upon two parameters, m dot and P2 by P1. So, the work requirement decreases either with the decrease in mass flow rate, that is m dot, or with the decrease in the compression ratio. Actually, this is a well known thing for thermodynamic students. This is what exactly is being exploited in a Linde dual pressure system. In a Linde dual pressure system, the work requirement decreases when the compression of a fluid is done in two stages and for different mass flow rates. So, if I want to go for a very high pressure, I will not go to that high pressure in one shot, but I will go in two stages, and this is again known as a compounding of compressor or having two or three different stages of compression. And also in each stage we will control the value of m dot. So, we want to minimize the work input to the compressor in such a way, or by playing with these parameters m dot and P2 by P1, and this is the real basics of this Linde dual pressure system. Now, how it is done we will see in the coming slides. So, here is a slide which shows you how a Linde dual pressure system works. So, as I said, dual means two, and we have got two compressors. This is what you can see from this particular schematic, and this is a Linde dual pressure system schematic. There are two compressors and two expanders. So, we have got two compression processes and we have got two expansions over here. At the same time, we have got two containers also. So, one can see a Linde-Hampson system having one heat exchanger and a compressor process and an expansion process. However, what we have is a two compressors, two expanders and two containers, and this is what a highlight of a Linde dual pressure system is. So, what does Linde dual pressure system has? The system consists of two compressors, a three fluid heat exchanger, and you can see in this heat exchanger you got one flow which is going down and one stream is going up and one stream is going up, and this is a very critical heat exchanger in this case, and this is called as three fluid heat exchanger. So, we got two compressors, three fluid heat exchanger, two Joule-Thomson expansion devices. So, we got a one device over here and we got a one device over here, making it a dual expansion kind of a system, and again two liquid containers and a makeup gas connection. So, you got a two connections, two containers, one over here, and here you got a makeup gas connection m dot f at this point. So, this is what a Linde dual pressure system is all about. In this system, the entire mass flow rate of the gas is not compressed to the required high pressure as was the case in our previous systems, and that is what a highlight of having a two-stage compressor. We do not compress the gas to the final pressure in one shot, but we do it with two compressors, In each of these compressor, we are playing with the mass flow rate also. As I said in the earlier slide, we can vary the mass flow rate as well as the pressure ratio across this compressor. So, we got a compressor number 1 and compressor number 2 over here. Now, as you see, I am talking about now the mass flow rates in each of these compressors. Only a part of the mass flow rate, that is m minus m dot I, which is coming from this side, is being compressed in a compressor number 1, is compressed to an intermediate pressure here, Pi. So, we have got two compressors, and at this point I get a final pressure, that is what is in my mind. I compress the gas equivalent to m minus m dot I at this point and compress it to some intermediate pressure Pi, and the next compressor compresses this gas at Pi to the final pressure at this point. All right. So, this is what a compression process takes place. Thereafter, that means at point 2, the mass flow rate Mi is added to the above stream and is taken and is then compressed from 2 to 3. So, here you can see I got one more stream coming from here after the first expansion. It joins the stream the gas flow at this point. The gas flow which is compressed at this point is m minus Mi. Having Mi joining this stream, what you have is a m dot over here. So, I am compressing full mass flow rate in the second compressor from point 2 to point 3, or from intermediate pressure Pi to final pressure P3 at this point. So, this is what is to be understood, that mass flow rate here is m minus Mi and mass flow rate here in this second compressor is m dot. The compression is from P1 to Pi or P2 and from P2 or Pi to P3 in the second compressor. This is the basics of lead-day dual pressure system. This arrangement not only compresses the gas in two stages, but also reduces the work requirement, and this is why we are doing all these things. Basically, we want to reduce the work done per unit mass of gas which is compressed. The stream m dot I along with the return stream from the container number 2 here is used to pre-cool the gas at point 3 in the 3 fluid heat exchangers. Now, the circuit is the gas when compressed up to the maximum value P3 gets pre-cooled by the return stream over here and by return stream over here. What is this return stream? This gas which is going to pass, or m dot which is compressed to the full pressure, is pre-cooled first in this heat exchanger and it undergoes the first expansion. And this expansion happens from value of P3 up to a Pi, and this is happening, the part of the gas or m dot I goes back. So, the return stream having m dot I goes back and it pre-cools the gas coming over here, all right. And from this gas or at this intermediate temperature and pressure, next expansion happen from Pi to Pf, or the lowest pressure which is P1, and here what you get is the m dot F, that is the fluid which is getting liquefied, the gas which is getting liquefied. So, this return stream will have m minus m dot F minus m dot I, because m dot I has already gone back, m dot F has already been taken off. The return stream will have m minus mf minus mi, and this is going to get compressed in the first heat exchanger when m dot F is added over here as a makeup gas, and this is how the whole cycle works. So, the pre-cooling heat exchanger is basically 3 fluid heat exchanger. It is getting pre-cooled by this return stream at intermediate pressure and this return stream at the lowest pressure at P1. It is important to note that 3 fluid heat exchanger has 3 streams with the 3 different flow rates. They are, as I just talked about, m dot which is coming from here, m dot I which is going back, and m minus mf minus mi which is going through this point. Now, most important thing, if I want to plot the whole cycle here, this is my TS diagram or temperature entropy diagram. The gas is compressed from 1 to 2 intermediate pressure, from 2 to 3 to the final destination pressure. Then gas is getting pre-cooled up to 0.4, which is over here at this point. The gas gets expanded from P4 to Pi or a P2 value here, and you can see the expansion process which is isenthalpic. The return gas m dot I goes back and joins the mainstream over here. The remaining gas, which is m minus mi, gets expanded further from 0.6 to 7 over here. Here we get m dot F, and the return stream has m dot minus m dot F minus m dot I, which goes back and the cycle continues. Now, this is the most important thing, that we have got 2 compression process 1 to 2 and 2 to 3, and we got 2 expansion process from 4 to 5 and 6 to 7. Okay. We got a return stream which is going at m dot I at 0.8 and return stream at m dot minus m dot F minus m dot I at point G, and this is how the whole TS diagram would look like. This most important thing is to plot this TS diagram correctly. Now, we will come to our routine job to sort of get expressions for the work input and the value of y. So, consider a control volume as shown over here and see what is going in and what is going out of this system. Okay. So, what is going in here is m dot at point 3, what is going out is m dot I at point 2, m minus mf minus mi at point 1 and m dot f at f over here. Applying the first law, we know all these things, getting the respective enthalpy values at those points, we write this expression. Okay, I will not go through this, all the enthalpy values are associated with all the mass flow rate over here, and if we reorganize the whole thing, what we get over here is m dot f upon m dot, which is nothing but y, is equal to h1 minus h3 upon h1 minus hf minus m dot I upon m dot into h1 minus h2 upon h1 minus hf. So, it is a very important expression, and you can see that there are two terms. Again, if we could denote m dot I upon m dot as intermediate mass ratio, m dot I upon m dot as I. So, it could be called as I, which is intermediate mass ratio. We have the liquid yield as m dot f on m dot is nothing but y. Y is equal to h1 minus h3 upon h1 minus hf minus I times h1 minus h2 upon h1 minus hf. That means that y is equal to this expression, and what you have is first expression, which is the first term is the yield for a simple Linde-Hampson system, considering that entire mass of the gas is compressed from 1 to 3. So, if you look at this first term, it is nothing but this, that is a simple Linde-Hampson system where the gas is compressed using one compressor from point 1 to point 3, and the yield in that case would have been this. However, it is not a Linde-Hampson system which is compressing the gas from 1 to 3, but we have got 1 to 2 and 2 to 3, and we have got m dot I joining at an intermediate point at an intermediate pressure, and therefore, we got a term called I. So, this second term takes into consideration the Linde dual pressure system, and it differentiates otherwise from Linde-Hampson system in which the compression will happen from 1 to 3 process. So, the second term is a reduction in the liquid yield occurring due to modification of the dual pressure system. All right. So, if one wants to understand, the first term indicates what would be the yield if the gas is compressed from point 1 to point 3 directly, and the second term actually brings it to the actual case of Linde dual pressure system. It deducts the value of y because it is a dual pressure system. All right. So, you will get less yield as compared to what it would otherwise have got in the Linde-Hampson system compressing the gas using one compressor from point 1 to point 3 directly. For the work requirement now, what we have done till now is finding an expression of y. But what is most important is what is my WC1 and WC2, which is the work input to the compressor number 1 and work input to the compressor number 2, and this is what will basically bring about the advantages we get in a Linde dual pressure system. So, we should first find out what is my WC1 and WC2. What you understand from here is for WC1, what you have is a mass flow rate of m minus m dot I, and what you have corresponding to that is a QR value, which is minus QR1. In both the case system, what is going in a system is m minus mi, what is coming out from that is m minus mi at point 2, what is going in is minus WC1, what is coming out is minus QR1. This is according to the direction and science convention we are going to follow with WC1 and QR1, as you all know. So, using first law, what we have is energy in is equal to energy out. So, what is going in is m minus m dot I h1 minus WC1 is equal to what is coming out m dot minus m dot I h2 into minus QR1, which is going to come out. Rearranging these terms, what we have is a QR1 minus WC1 is equal to m dot minus m dot I h2 minus h1. By second law, we got a value of QR1, and we know that QR1 is equal to m minus mi T1 into S2 minus X1, TdS basically multiplied by the corresponding mass flow rate. If we put this expression of QR1 in this, what we get is WC1, which is equal to m dot minus m dot I into T1 S1 minus S2 minus H1 minus H2. So, you can see that what is the mass flow rate in the first compressor m dot minus m dot I multiplied by temperature into delta S TdS minus H1 minus H2. This expression is similar to what we have had earlier for a compression process. If I go to the second compressor now, what is the flow rate through that is m dot. The second compression has full mass flow rate of m dot, and corresponding value of entropies and enthalpy have to be taken into account. The mass flow rate across the second compressor is m dot. Following the similar procedure for the work requirement for the compressor 2, what we get is minus Wc is equal to m dot into T1 into S2 minus S3 minus H2 minus H3, because the process WC2 compression process is happening across point 2 and point 3, and we are taking the entropies and enthalpies related to those points. So, this will form the work of compression for the second compressor. Now, the total work requirement is given by Wc is equal to Wc1 plus Wc2. So, the total work is not now going to be determined by what is the value of Wc1 and what is the value of Wc2. Wc1 depends on what is the gas, what is the amount of gas which is getting compressed in the compressor number 1, and what is the pressure ratio across point 1 and 2, all right, P2 by P1. Similarly, Wc2 depends on what is the mass total m dot going into it and what is the pressure ratio across it, 2 and 3. It is this Wc1 and Wc2 which makes a difference to the value of Wc or the total work of compression, and this is the most important to understand, because by doing this Linde dual pressure system, we are basically trying to minimize the work of compression in this case as compared to a simple Linde-Hampson cycle. Denoting the ratio, now if we add both the expressions together and if we put the value of I in that expression, we get work per unit mass of gas compressed, that is Wc by m dot, as this expression, that is T1 into S1 minus S2 minus H1 minus H3, as if the whole thing is getting compressed from 1 to 3 part, which is what we saw in expression for Y. In the similar line, again you have got expression for Wc by m dot. First term denotes as if the whole thing is compressed from 1 to 3, and the second term denotes, depending on the value of I, what is to be deducted from it, that is I into T1 into S1 minus S2 minus H1 minus H2. This much of work will be done less as compared to the process of compression carried from 1 to 3 process. So, same thing is written. The first term is the work requirement for a simple system, considering that the entire mass of the gas is compressed from 1 to 3. The second term is the reduction in the work done, work requirement occurring due to the modification, and this is what we basically are going to exploit in order to reduce the work done per unit mass of gas which is compressed. With this background on Linde dual pressure system, Linde dual system, as I said, we have just derived expressions for Y and the power input, compression power basically. I want to now take you to understand what is the effect of various parameters on these parameters. So, what I am going to do is, I am basically giving you a tutorial, and we will solve this tutorial and understand from this how these parameters play a very important role in order to get expressions for what is the work done, what is the work of compressor per unit mass of gas which is compressed, and things like that. So, this tutorial is the most important tutorial. So, what is the problem to understand is, determine W by m dot F and figure of merit for a Linde dual pressure system with argon as a working fluid for the following intermediate pressures. The system operates between 1 atmosphere and 120 atmosphere, and the intermediate mass ratio I is 0.6. There are various intermediate pressure points, that is 0.2, and in this problem we want to understand what is the value of W by m dot F and figure of merit for these intermediate pressures. So, I am going to compress the gas first from 1 bar up to 4.05 bar and solve all the values to get what is the W by m dot F and figure of merit for that case. Then I will get the second value of pressure 20.3, 75.9, 101.3, and in such a way that my final pressure always remains at 120 atmosphere. All right. So, here I want to understand what is the effect of this intermediate pressure. So, first of all we should calculate how much work per unit mass of gas which is liquefied one gets at different intermediate pressure. The intermediate mass flow ratio I is in this case 4.6. Then my tutorial also want to understand what will happen if I go from I value of 0.6 to 0.7. So, repeat the above problem for I is equal to 0.7 and ultimately plot the data graphically and comment on the nature of Y W by m dot F figure of merit versus I. all right. So, is basically I am trying to understand what is the effect of intermediate pressure on W by m dot f and figure of merit, and what is the effect of value of I or the mass ratio 0.6 and 0.7 on all these studies. So, there are intermediate two problems in order to understand the effect of intermediate pressure and effect of I on these important parameters, all right. This is my problem. So, what is given in this particular problem is we want to work on a Linde dual pressure system. The working pressures are from 1 atmosphere to 120 atmosphere. The working fluid is argon. Now, this is very important that one should have all the properties of argon. The temperature is 300 Kelvin, that means the process of compression is carried out at 300 Kelvin. The intermediate mass ratio is 0.6 and 0.7. For above system, calculate work per unit mass of gas liquefied, that is W by m dot f and figure of merit. And the intermediate pressures are 4, 20, 75, 101 atmospheres, all right. So, this is my problem. What is the methodology? The methodology is for solving in this particular class is the two mass ratios I condition under study are 0.6 and 0.7. In this particular tutorial, I am not going to repeat the calculations for each of these values. I am going to demonstrate to you how to calculate these values for one pressure and for one I value, all right. What I expect you to do is then carry out this exercise further for all the pressures and for both the values of I is equal to 0.6 and 0.7. So, in this tutorial, the liquid yield Y and work plus unit mass of gas liquefied at W by m dot f are calculated only for I is equal to 0.6 and 4.05 bar or 4 atmosphere as intermediate pressure conditions. So, I am just solving one problem for I is equal to 0.6 and P2 or Pi is equal to 4 atmosphere, while what I am leaving it to you is to calculate I is equal to 0.6 and all the pressure, and then I is equal to 0.7 and all the pressures for yourselves. However, in the final destination or in the final slides, I have got values for all these calculations. So, we have done all this calculation ourselves, and what we want you to do is to check your calculations so that you also get those values, saying that your calculations are correct. It is basically an exercise for you. All other calculations pertaining to value of I is equal to 0.6 and 0.7 and for all other intermediate pressures conditions are left for you as an exercise to the students, all right. Okay, so, let us go for I is equal to 0.6 and P2 or Pi is equal to 4 atmosphere. So, before, as you all know with earlier problem, first we want to do ideal cycle analysis, and therefore, we got a ideal thermodynamic cycle from which we will get ideal work requirement, and this is very important to calculate the figure of merit. For ideal work requirement, this is the formula W I by m dot T1 into S1 minus SF, H1 minus HF, and here as you know whatever is compressed is getting liquefied. So, once we know 1, we know the point F also. So, pressure is 1.013 bar, temperature is 387.3, which is the boiling point of argon at 1 atmosphere. The enthalpy values are given at 0.1 and F, the entropy values are given at 0.1 and F. If you put these values in this equation, what you get is Wc by m dot work of compressor per unit mass of gas liquefied is equal to 461 joules per gram. So, this is my first basic calculations which we do almost for all the problems. Now, coming to our problem, that is Linde dual pressure system, and this is our schematic. In this schematics, the enthalpies and entropies one should get from the TS charts for argon, all right. So, get those charts for argon and get the enthalpy values. So, here you can see 0.1, 2, 3 and F. These are the values which are required for our formula where we require enthalpy values and entropy values. Now, where are these points? The point 1 is at 1 bar 300 Kelvin at this, where m minus m dot I will be getting to compressor number 1. Point 2 is the intermediate pressure or after the first compression, which is this point. The point 3 is over here and the corresponding properties are given. Now, point 2 is going to be at 4.05 bar, while point 3 is going to be at maximum pressure, that is 120 atmosphere or 121.5 bar, and again point F is going to be the last point at this, which is going to be at again 1 bar. So, one should check all these values at 1 bar, 4 bar and 3 bar, 300 Kelvin, 300 Kelvin, 300 Kelvin here. while at point F it is 87.3 Kelvin. Corresponding value of enthalpy is 349, 348 and 326. So, one can understand that as the pressure increases, the enthalpy at the same temperature at 300 Kelvin, temperatures are same over here, the enthalpy decreases. Okay. Corresponding to, again similar thing happens with the entropy. As the pressure increases, the enthalpy and entropy values are decreasing over here. So, these are the 4 different points, and now what we want to see is take the enthalpies and entropies of this value and put in the equation. So, corresponding temperature entropy diagram is 1, 2, 3, 4. So, 1 compression from 1 to 0.2, 1 bar to 1 atmosphere to 4 atmosphere, which is intermediate pressure, 4 atmosphere to 120 atmosphere, which is the maximum pressure over here. The TS diagram for linear dual pressure system is shown here. The compression process is from 1 atmosphere to 4 atmosphere and then from 4 atmosphere to 120 atmosphere. So, you got a WC1 over here from 1 to 2 and WC2 here from 2 to 3 in this case, and respective points are given over here in this TS diagram. Now, let us first calculate the liquid yield, which is this expression. As you know, we got a first term and a second term. What we want to know is now enthalpy at point 1, 2, 3 and F, and we have already made those tables. We will get the points enthalpies at H1, H2 and HF, and of course, H3 also. So, the first is argon I is equal to 0.6 at this point, which is intermediate pressure of 4.05 bar, and the corresponding values are given over here 1, 2, 3, 4, all the temperatures 300, 300, 300, 87.3, corresponding enthalpy values, corresponding entropy values. If you put those values in this formula, what you get is 0.0817. So, Y for I is equal to 0.6 and intermediate pressure is equal to 4 bar or 4 atmosphere, we get the value of Y to be equal to 0.0817. That is my calculation. As I said, I am going to do this calculation for only one I and one pressure, which are these two values over here. Now, let us complete all the calculations for this particular value. So, now let us calculate work per unit mass of argon compressed for I is equal to 0.6, and this is the expression. Again, we have got T1 into S1 minus S3 minus H1 minus H3 minus I times T1 into S1 minus S2 minus H1 minus H2. Putting these values from this table, if I put this value, I get WC upon m dot is equal to 235.6 joule per gram. This is work done per unit mass of gas argon compressed. Now, I want to calculate work done per unit mass of argon liquefied, for which what I want to know is WC upon m dot, and I want to know what is the value of Y, which is 0.0817, which is what we have just calculated. What we know is WC upon m dot F is equal to WC upon m dot upon Y. All right. So, what we have is both the values, this upon this will give you WC upon m dot F. So, I will do 235.6 upon 0.0817, which is equal to 2883.7. This is my work done per unit mass of gas argon liquefied, which is rather high as compared to the ideal work input which we had seen earlier in the ideal thermodynamic cycle. The figure of merit is equal to Wi upon m dot F, ideal Wi upon m dot F divided by actual Wc upon m dot F, which is what Wi upon m dot F is 461 from ideal thermodynamic cycle, and if I put those values, what you get is figure of merit is 0.1598. So, here we have got all the values calculated so far, that is Y and figure of merit, Y and WC, Y and total work done, and of course, the figure of merit. Now, I would like to calculate all these values for all the intermediate pressures, and without giving the details of those calculations, I will give you a table which will have all these values. So, tabulating the result for I is equal to 0.6, we have the following comparison for the various values of intermediate pressure here. So, intermediate pressure is 4.05 bar. So, case number 1, 2, 3 and 4, this table gives for all the intermediate pressures, that is 4 atmosphere, 20, 75 and 101 atmosphere pressure as the value of P2. The final value of the P3 is always 120 atmosphere, and you got a value of Y, W by m dot, work done per unit mass of gas compressed, W by m dot F, work done per unit mass of gas liquefied, and figure of merit. What you can see from this table is, I will talk about each of these vertical column in detail in the next slides, but what you can see is as the intermediate pressure increases, if the entry pressure and exit pressure remain the same, and if the value of intermediate pressure, if it is increased, the value of y has started decreasing. So, 0.08, 0.07, 0.05 and 0.04 are the values of y. That means, the value of m upon m dot f upon m dot has decreased, the yield has decreased if we increase the intermediate pressure, but the value of w upon m dot has decreased. 273 minus 172, 235, 172, 118, 111. So, this value has decreased. What is interesting to see is the value of w upon m dot f, that is work done per unit mass of gas liquefied. What you can see, this has come down from 2883 to 2295 and again started increasing. So, it is decrease over here, but then there is a increase over here. It means that it has gone through a minima, and similarly to that, what we get FOM, figure of merit, we have got 0.15, 0.2008 and 0.2 and 0.17. That means, FOM goes through a maximum, and this is what we will see in the next slide. So, what you understand from here is as the intermediate pressure increases, y decreases, w by m dot decreases, but w upon m dot f goes through a minima and figure of merit goes through a maxima. This is what is the output of all these value for I is equal to 0.6. Now, the same study is done at 0.7 also. When I is equal to med equal to 0.7, we have carried out the same studies, and the results for I is equal to 0.7 for the various intermediate values is this. So, again you can see now, as the intermediate pressure increases from 4 atmosphere to 20 to 75 to 101, y again decrease from 0.08, 7, 4 and 3. W upon m dot, that is work per unit mass of gas compressed, decreased from 228 to 154 to 91 to 83, but W upon m dot f, work per unit mass of gas liquefied, again went through a minima. The minima is happening possibly between 0.2 and 0.3, case 2 and case 3, and it is maximum over here, goes down, reaches a minima and starts going up over here. The figure of merit again goes through a maximum somewhere at between the case 2 and case 3. So, again it follows absolutely the same trend as what it was for I is equal to 0.6. Now, here as I said, we have carried out only one exercise for 0.6 and 4.05 bar. What I expect all the students to do is get this table calculated by yourself, get the earlier table also calculated by yourself, and then plot it, and then you start understanding what exactly happens and why it happens. All right. So, all these things has been left for you as an exercise. While I have just got all these value calculated, I am putting in front of you. So, this may serve as the answers for you, while I expect you to solve this as a problem or as an assignments for you to see that you can read the values of enthalpy and entropy properly. Now, what is important is to understand why it happens. I mean, plotting this or calculating this value is not a big deal, but what I want you to understand is what happens when I go from 0.6 to 0.7 as I values, and for a 1 I, why if the intermediate pressure goes on increasing, why the value of y decreases, why the value of w by m dot decreases, why the value of w by m dot f goes through a minima, and why the value of FOM goes through a maxima. All right. So, this is the most important thing for the engineers to understand. So, let us now therefore, whatever table I have just shown you, let us try to plot this table graphically, and therefore, the understanding will be much better. So, first table we will calculate is liquid yield y versus I. So, what I am showing here you are the two axes. On the left side you got w by m dot, and the right side you got a y. In the first this thing right now, you understand what is the relationship, and on the x axis what you have is the intermediate pressures, which are varying from 2 bar to 102 bar atmosphere. And let us compare the, as you increase this intermediate pressure, what happens to the value of y, which is on the right axis, okay, right y axis, do not see at the left y axis. So, see whatever points we have got, let us plot those y values versus the intermediate pressures. So, this is my table for I is equal to 0.6. So, if I plot these points, the first point 4.05, 0.08. So, if you see on the right axis 0.08 value and 4 bar, the second value, third value and the fourth value. Alright. So, if you join them together, you can see kind of linear variations when you plot y with respect to the value of intermediate pressure, and this is the value for I is equal to 0.6. We got a second table for I is equal to 0.7, again get those values of case number 1 over here, case number 2, case number 3 and case number 4. So, if you could plot these values and connect them, you can see this. So, this is to be compared with the value. So, what do we understand from this particular graphical graph? That as you go on increasing the intermediate pressure, the value of y decreases. This is exactly what we saw in the earlier table. So, for a given value of mass flow ratio I, the yield of the system decreases with the increase in intermediate pressure. Why does it happen? Now, if you recollect the expression for y, we got the first term and the second term. What you understand, second term has a negative value, which is h1 minus h2, which has a numerator as h1 minus h2 and it has a negative sign. As you understand that, as the value of P2 or the Pi increases, this second bracket starts increasing and therefore, the value of y decreases. Alright. If the intermediate pressure increases, it means that mathematically the expression for y whatever we had, the second part which was I times one bracket, that bracket has a numerator which was h1 minus h2 and this value starts increasing, alright, and therefore, the negative part start increasing and therefore, the value of y decreases as you go on increasing the intermediate pressure. The second aspect to understand for this is, as the intermediate pressure increases, the intermediate temperature in the TS diagram also will increase. The intermediate temperature in the dome also increases. Alright. If you remember, there is a dome and we got a point intermediate pressure temperature corresponding to the intermediate temperature also, and this intermediate temperature starts moving to the critical temperature value, or it is starts going up the dome, and therefore, when the second expansion happens, it will happen from this intermediate temperature, and again at this point, the point after the expansion will fall towards the gas region, and therefore, if you increase the intermediate pressure, the intermediate temperature from which the second expansion happens, that also gets lifted up, corresponding to which the point after the second expansion falls near the gas side. Therefore, again you will get the less y value, and this explains why if you increase the intermediate pressures, you will get less y in those cases. Also, as the mass ratio I increases, that means if I go from 0.6 to 0.7, the yield of the system decreases. Now, understand again, if my intermediate gas ratio increases, that means 70%, for example, I is equal to 0.7, 70% of the mass flow is going back. It means that only 30% of the gas is going for the second expansion, all right, and the liquid yield is going to come from this 30% only. It means that more the gas goes back, more the value of I is, the m dot f is always going to be less, because the second expansion has only 30% of the gas which is compressed. All right. So, as the value of I increases, less and less gas is going to go for the second expansion, which means less and less yield. All right. So, corresponding to that, however, the work per unit mass of gas which is going to be compressed is going to be becoming less and less, but the value of Y effectively is going on reducing, the value of I increases. So, as the mass ratio I increases, the yield of the system decreases, because the mass of the gas actually expanded in JT device decreases, and this is the reason that as I increases, the Y value will decrease. Now, let us plot the second parameter, which is W by m dot upon R versus I. All right. So, the plot between W by m dot versus I for this value is over here. So, we got various values, and you can see that as you go on increasing the value of intermediate pressure, the W by m dot decreases. What is important to note is the slope of this is much higher initially, while it is less and less as you go for higher value of intermediate pressure. The maximum value of P3 is always 120 atmosphere. This was the case for I is equal to 0.6. As you go for I is equal to 0.7, again similar trends you can see, but here W by m dot is still less. That means, if you increase the intermediate ratio 0.6 to 0.7, the W by m dot further decreases. But again you can see that the slope here is very high initially and it flattens down as you go for higher intermediate pressures. Alright. So, this can be definitely understood that as you go on increasing the intermediate pressure, your WC1 and WC2 will change. The WC2 will have only m minus m dot I which is compressed, while WC2 will have all the m dot which is going to be compressed. So, as you go on increasing the Pi, the pressure ratio for the second compressor is less and less, while the pressure ratio for the first compressor increases. Corresponding to that, the value of WC1 and WC2 change, but if you go on increasing the value of intermediate pressure, alright, the whole mass which is getting compressed actually is in the compressor number 2. So, the second compressor is now subjected to less pressure ratio and therefore, the value of WC2 in this case gets less and less. Alright. So, as you go on increasing the intermediate pressure ratio, the value of WC2 decreases and therefore, if you add both of them together WC1 plus WC2, the value of work done per unit mass of gas compressed goes on decreasing if you go on increasing the intermediate pressure. This we will have to understand with all the logistics which I am just talking about. What happens to WC1, what happens to WC2. As you go on increasing the intermediate pressure ratio, the pressure ratio for the first compressor increases, but it is subjected to less mass flow rate. While the pressure ratio for the second compressors gets reduced, but it is subjected to maximum mass flow rate. So, it is a net addition of WC1 and WC2 which will determine what is the value of W by m dot in this case. Okay, now, for a given value of mass I and W dot, the system decreases with the increasing intermediate pressure. As the mass ratio of I increases, the W by m dot decreases because the more of the mass flow rate is bypassed from compressor number 1. So, if we increase I now, your work WC1 now in this case will decrease, while WC2 will remain the same, but WC1 will decrease because the least mass is going to the compressor number 1 in this case. So, you can see the relative curve in both the cases, that is Y curve and W by m dot. It is important to note that initially the slope of W by m dot is much steeper than that of Y. Later on, as the intermediate pressure increases, the slope of Y is steeper while the slope of W by m dot decreases in this case. What is important now is to understand W by m dot f versus I, which depends on both these behavior of Y and W by m dot, and these are the values. So, if I plot these values 1, 2, 3 and 4, and if I join them, what you can see is the clear cut minima between this point over in these two cases. And again for I is equal to 0.7, if I put those values, alright. So, this is the whole exercise is carried out in order to choose a point of intermediate pressure for which W by m dot is going to be minimum work of compression per unit mass of gas liquefied. Alright. So, this is the 0.6 case and this is the 0.7 case. Alright. So, this is the most important curve which we get from the values of division of W by m dot divided by Y, because the plot of the W by m dot f value is determined by W by m dot divided by Y. So, mathematically as you understand, W by m dot f is nothing but W by m dot upon Y. W by m dot f being the ratio of W by m dot and Y, the relative decrease in the numerator and denominator determines the slope of the value of W by m dot f, and that is why the ratio is, the curve nature is like this. For a mass ratio of I, W by m dot f decreases with the increase in the intermediate pressure. Alright. So, we got it goes through a minima and it decreases first, goes through a minima and again starts increasing. The work falls to a minima and then increases with the increase in the intermediate pressure, and you can find that for this case 0.6, one should operate at a pressure somewhere around 50 bar, 50 atmosphere, while somewhere around 62 is the corresponding optimum pressure for I is equal to 0.7. The working point is compromised value of Y and m dot. So, as you know that as you go on increasing the intermediate pressure, the value of Y falls down, while the W by m dot f is touching minimum at these two values. Therefore, what value of Pi one should select is actually going to be compromise between what Y you want, corresponding to that what W by m dot you might get. So, what is your liquefaction requirement and what should be your W by m dot f? This is a compromise value one has to select in this particular case. All right. So, depending on your liquefaction requirement, corresponding W by m dot minimum we should be selected. The figure of merit is also plotted from the same thing, and exactly reverse will happen. The wherever there is a W by m dot f minimum, you will get a maximum. By the definition, that definition of figure of merit, you will get a maximum W by m dot f here, and for 0.7 case, I is equal to 0.7 case, you will get a value of figure of merit as maximum as around 62 bar somewhere here, and as I said around 50 bar somewhere at 0.6, and this is the value one should select if one has choice, or one has to compromise, and on this top portion and corresponding to those values, the value of Pi should be chosen. All right. So, for a mass ratio of I, the figure of merit increases with the increasing intermediate pressure. With the further increase in the intermediate pressure, the figure of merit reaches a maximum value and thereby it decreases. It is important to note that the figure of merit reaches a maximum value at the same intermediate pressure at which W by m dot f reaches a minima for a given value of mass ratio I. This is what I just talked about. With this background, with all this, the way the tutorial has been solved, I got an assignment for you, and assignment solving, only this will make you perfect. So, what I want you to is understand, solve the problem again for argon for different pressures of 1 bar and 200 bar. Now, intermediate mass ratio is taken as 0.6, and we have given the answers also for this case for Y, W by m dot, W by m dot f and figure of merit. So, please do this exercise and check your answers, check your calculations to get these answers. In summary of this particular lecture, the Linde dual pressure system is a modification of a simple Linde-Hampson system in order to reduce the work requirement. All right. The Linde dual pressure system is never to increase the yield. All right. In fact, you know that the yield decreases with the intermediate pressure increasing. The Linde dual pressure system is basically aimed at reducing the work requirement per unit mass of gas compressed or per unit mass of gas liquefied. In this system, the entire mass flow rate of the gas is not compressed to the required high pressure as was the case in the previous systems. All right. In this system, the work requirement decreases when the compression of fluid is done in 2 stages and for different mass flow rates. This is the most important thing. The pressure ratios for the compressor number 1 and compressor number 2 are going to be different. At the same time, the mass flow rates in the compressor number 1 and 2 are going to be different. The yield of the system is given by the following equation, which is this. As you know, Y is equal to H1 minus H3 upon H1 minus HF minus I times H1 minus H2 upon H1 minus HF. The work requirement also is given by this expression, as if we are going to compress from 0.1 to 0.3 and then reducing the work in the ratio of I from 1 to 2. In the above expressions or the equation, the first term corresponds to the Linde-Hampson system and the second term is the reduction occurring due to the modification. So, basically the first term in both the cases is as if we have got a Linde-Hampson system from 0.1 to 0.3, which is normally not possible. One cannot compress from 0.1 to 0.3 directly, and therefore, what we are doing is reduction which is happening in value of Y and WC by m dot because of the modifications of the Linde dual pressure system. For a given value of mass ratio I, the Y and W by m dot of the system decreases with the increase in the intermediate pressure. This is just what we saw in the tutorial answer sheet, where as you go on increasing the intermediate pressure, the value of Y and W by m dot decreases. For a value of mass ratio of I, W by m dot f passes through a minima as the intermediate pressure increases. So, this is a minima which we want to attack. Basically, at what pressure, at what intermediate pressure one gets minimum work done per unit mass of gas which is liquefied. We want to attack that minima which will ensure that you are doing minimum work of compressor to get the work of liquefaction per unit mass of gas which is going to be liquefied. On the other hand, for a mass ratio of I, the figure of merit passes through a maxima with the increase in the intermediate pressure. Right. All right. So, when you attain minima over here at the same particular pressure, we attain maxima for the figure of merit. The operating point of the system is a compromise value between Y and W upon m dot f. As you know, As you go on increasing the intermediate pressure, the value of y decreases, but the value of W by m dot f will fall through a minima. So, one has to take an optimum value between these two. In fact, one should design to get W by m dot f minimum. Corresponding to that, your desired y value should match. So, whatever my desired value of y is, I should get W by m dot f minimum at. It is important to note that the figure of merit reaches a maximum value at the same intermediate pressure at which W by m dot f reaches a minima for a given value of y. Thank you very much.